All right, happy Tuesday, everybody. I hope everyone enjoyed this beautiful rainy day and got to get out in the rain this morning. What a lovely way to start the day. A couple of quick notes today. The number one is massive thank you to all of you, seriously, for doing the drill. I cannot overstate how important that is for us for figuring out what concepts y'all are struggling with, what things are still confusing, what things are going smoothly. It really, really helps us figure out how to shape both sections and in particular what we're doing here in our class sessions. So we really, really appreciate y'all filling those out. I'm going to quickly reflect on some of the things that I noticed from the drill. We'll go through those. So one thing that I thought was really interesting was over 95% of y'all have never touched OCaml before. I thought that was really cool. That was not unexpected. That is what we normally expect. But it is totally normal to be in this class and never have used OCaml even for a single moment before. And so just if you're trying to get a sense of where other folks are at with that, that's the situation there. In fact, very few had actually used functional languages before, so I thought that was also quite interesting. A couple of questions about the collaboration policy that I just wanted to make sure we're all on the same page on. Most people were totally on the same page about this, but I just wanted to double check and check in about it. So particularly the stuff that people seem to struggle with was this idea of looking over a friend's shoulder and when that's okay or not. And I totally get that, and it is kind of complicated. And so obviously the safe answer is to just not do it, right? Like that is sort of the easy way to make sure you're on the safe side. But in particular, if you are not writing code at the same time, it could be safe. So especially like if you have already submitted your homework, and so there's no way that you might see something over your friend's shoulder that would then change how you are actually going and writing your own code, that would be an example of a quite safe situation. And then also, folks were curious about snippets from Stack Overflow. It is fine to put in small snippets, right? If you are copying over large chunks, we start to get worried, but if it's just a couple lines, we're not too worried about that. And then a quick note on how to prevent autograder runs. So if something happened and you're like, oh man, I shouldn't have done that. I want to withdraw my homework assignment. The way that you do that is you go ahead and you overwrite what you had submitted with the original starter code, and we will treat that as a withdrawal. So that's the thing that you can do to actually prevent your code from getting graded. Okay. In terms of the things that are confusing to folks right now, it's basically exactly the things that we would have expected. So the main thing that's coming up is, OCaml is still really weird and confusing, and that's totally natural, and I think as we're getting more hands-on experience with it, it's gonna get less and less confusing. But that seems to be the main thing that's tripping people up right now. Totally makes sense. We're gonna keep getting more practice with it, so hopefully that's gonna get smoothed out a bit over time. Okay, one more logistics note, and then we'll dive in on content for the day. So apparently, GitHub Classroom specifically, is having some issues. We are so sorry. We wish we controlled GitHub Classroom. We do not control GitHub Classroom. But what this means in the meantime is that I'm going to ask you all to please make sure that you have access to the starter code as early in the week as possible. So in fact, maybe today, go ahead and try to check out the next homework. Make sure you have access. If you do not have access, our very kind GSIs have done an awesome thing and gotten up a special form that's just for please make me have access to this homework. And so you can go ahead and use that form if you are lacking access. But we do want to make sure that people are checking early, because it does seem like, at least for now, until GitHub Classroom fixes whatever this issue is, there's still some amount of manual work for the GSIs to make sure that everyone has access. Hopefully most people are getting access by default, but if you are running into problems, there are some manual fixes that the GSIs can do for us. Okay, that's our general logistics update for the day. Cool. So in that case, we have a couple of exciting topics for today. I'm going to introduce us to a new slide from our slide deck. How am I going to do this? Let's see. We'll look at the compiler for a second. No, we won't. That's not mirroring. Great. We can look at our compiler for a second while I get us looking at the right slide. So here, we have our great big CS164 summary slide. We actually have two of these. And this is touching on basically all of the topics that we are excited about getting to over the course of the semester, the kinds of topics that we are going to see on the exam. And occasionally I will take a moment to just stop and highlight the ones that we're going to tackle for a given day, just so you have a sense of what's coming up. And so here are the things that we are tackling today. So we're going to go ahead and, you remember we talked about interpreters versus compilers last time. Today we are going to be talking about this. What are the various components of a compiler? We're going to talk a lot about syntax versus semantics. We're going to talk a bit about assembly, right, as we often do. And we're also going to talk a little bit about intermediate representations, although we are not today going to talk about LLVM-like low-level intermediate representations. So those are our general topics for the day today. So far, so good. OK, so let's go ahead and swap back just long enough for us to get to the slides we are mainly dealing with. So today, we're going to be doing unary operations. They are going to look something like this. But before we dive in on that, I'm going to ask you to go ahead and consider these two programs. And the thing that I want you to consider is, with someone nearby, go ahead and chat about, based on sort of the programming languages you know, the programming languages you're familiar with, would you expect that these two programs are going to behave the same? Go ahead and chat for 30 seconds to a minute. All right, I want you to go ahead and hum if you think these programs are going to behave the same. I want you to go ahead and hum if you think they're going to behave differently. OK, cool. Yeah, so I actually like both those answers. The first answer I like a lot because based on all of the programming languages I have interacted with, my first prediction, my initial prediction of what is likely to happen if the language that I'm seeing is similar to the languages I've seen before is that these will behave the same. So that seems like a really good answer. I also like the second answer, and that's because nothing about what we're seeing actually tells us anything without knowledge of the language we're working in, actually tells us anything about what these programs will do, right? For all I know, that when you see this program, it could be that the language is implemented in such a way that it's going to print out the string unicorn. And that's totally fine, right? Like that could be the correct behavior for this program, depending on what the language has chosen to do with this program. And so this gets at an idea that we are going to be thinking about over the course of today, which is the difference between syntax and semantics. So syntax is what the program looks like, right? These two programs are using different syntax. We can see that in order to write down something that could be the same program, they've written down different strings of characters. So they're using different syntax. But if they behave the same, if they do the same thing, then it is possible that the underlying language actually is using the same semantics. So the behavior of the programs could be the same. And so this is going to bring us to talking about the components of a compiler. And it's a little weird in some ways that we're only getting to this right now. This is often what you will see the very first day of a programming languages and compilers class is sort of this diagram. And you'll see sort of the various different components of a compiler. And often that's happening because the first thing you're going to do is build this arrow. And then the second thing you're going to do is build this arrow. And then you'll build this one. And then you'll build this one, right? And so that's how they're often structured. Whereas in fact, what we have chosen to do is always have this full pipeline available to us. But we'll start with a very small language. We're going to start with something small, and we're going to add another programming language feature, and then another programming language feature, and another programming language feature. And so we will be able to run this entire pipeline the entire time, but we'll be expanding the language for which we can do it. But I do still want to talk through what's actually happening at each of these. So let's put some names on each of these arrows And let's actually go ahead and figure out what is happening inside. So the first thing we need to do is go from the source code, which is coming to us as a string, and turn it into tokens. Now we're going to talk a lot more later on about what we mean when we say tokens, but basically individually meaningful components of our program, right? If we see the number 1 in our program, then 1 could be a token. If we see the number 13 in our program, then 1 on its own, within the context of that 13, is not going to be a meaningful token, but 13 would be. So let's go ahead and call this the tokenizer, as you might have guessed. And you may also hear this called the lexer. Then the thing that's in charge of going from this list of tokens, this unstructured list of tokens, to some kind of representation of the program that we can freely manipulate, which we will be calling the abstract syntax tree, that is going to be the parser. And in addition to going from that list of tokens to that tree representing the program structure, the other thing that will be happening there is we'll be figuring out if the list of tokens we've got is actually a thing that is allowed to exist in our language or not. So that's the other thing the parser is going to be in charge of for us. So we'll go ahead and call that entire thing, all of this, is going to be the front end, right? So this is the thing that is in charge of going from the syntax, right? That particular character set that the programmer wrote down, turning that into some kind of structured representation of the program, that is the front end of the compiler. So far, so good? Cool. In that case, let's turn to what you have probably guessed, based on what I just wrote. What you've probably guessed is called the back end of our compiler. And here we've got code generation, right? So this is where most of the stuff that makes compilers hard, that makes compilers interesting, lives. And so we are going to spend at least the first half, maybe even a little bit more, of our semester on this, because this is where the core challenges live. And we will eventually be shifting over to, let's see, can we highlight, to this portion at about the halfway mark, and then we'll explore some other topics as well. But a huge amount of the time is actually going to go to this, where the really big challenges live. And then this next arrow isn't actually super interesting, but someone's got to do it. So we've got the linker, we've got the assembler. And all of the stuff that's going there is turning something that's already quite low level, right? So our assembly instructions are already pretty low level into something even more low level, which is to say ones and zeros. That process is basically mechanical, so none of the hard stuff really lives there, and we won't actually bother to make our own thing for turning things into ones and zeros. But if you're interested in it, please do come chat. And so this, on the surface of it, looks like a complete compiler, right? If we can go down this path, we can follow all these arrows, we have everything that we need in order to go from a program that the programmer has written, they've typed it into their text editor, everything we need to go from that to something we can run on the machine. But actually, this is not all that we have in your average compiler. Well, okay, maybe not your average compiler. I wouldn't want to talk about the average compiler. But in your production compiler that you have all used, you're going to have something else. So you're going to go ahead and have optimization. So let's go ahead and write opt1, and maybe opt2, and maybe, in fact, opt3. So often you have a bunch of optimization passes that you are running on some structured representation of your program. And you're doing all kinds of transformations at that stage with the intent that the program that finally comes out the other side is going to run faster, or it's going to run with a lower memory cost. Doesn't necessarily, do the same thing depending on what kind of thing you are trying to optimize, right? There are multiple different things you might be trying to optimize, and you might then choose to run different optimizations as a result. But this is sort of what's happening in optimization. And in fact, even once we have generated instructions, we're not necessarily done with optimization even then, because it turns out that we can do something called peephole optimization, which is actually going to do optimization on sequences of assembly instructions, right? So we can go ahead and do a bunch of things, and all of these together, right, are going to be optimization. So typically, you are going to have some kind of optimization in a realistic real-world compiler. And so what we are going to be doing over the course of the semester is spending a bunch of time here, basically throughout, right? We're never going to get away from needing to do interesting things on the code generation side. And then for a little while in sort of the middle part of class, we'll switch over to talking about tokenization and parsing and how we can actually get from the surface syntax of the language, the thing that the programmer is actually typing into their program editor, to this structured representation of the program that we're actually going to want to play around with. And then once we've covered those topics, we'll switch on over to optimization. We'll talk about what's happening inside the optimizer. But I want to emphasize here that the only thing we actually need in order to actually run programs is this path, right? If we've got this path covered, we don't actually need optimization. We can go ahead and actually run programs just based on having those arrows that I highlighted available to us. So are there questions about these overall components of our compiler? Yeah?
Can you give us like a brief inlay on like what optimization might look like, especially if you're running like several times?
Can you give me a brief? Okay, so I think this is maybe a question about the fact that there are multiple optimization arrows coming out and going in. Oh, I love this question. Yes, so there are a bunch of different optimizations that we might want to run. And this isn't just about the fact that we might want to do some optimizations to reduce memory footprint and some optimizations to make the code run faster. Even if we only care about something like making the code run faster, there are so many different optimizations that we might want to run. So many that, in fact, one of the huge issues in compiler optimization construction is actually figuring out the order in which to run them, because even that can matter. And this is one of the sort of the big open problems in optimization land, is how do we even sequence these? Right? So this general problem, in fact, this sort of whole section here is sort of the main work that is happening in compilers research right now, is how do we make things that are even more optimized? There are other things happening, right? There's a little bit of an overstatement, but this is definitely still a hugely active area of research of how do we make optimizers even better. Hopefully that gives a general sense of why we might have multiple optimizations and why we would be running things through the optimization multiple times. We might, in fact, run even the same optimization multiple times, but we'll get to that later. Yes? Oh, sorry, AST stands for Abstract Syntax Tree. And so basically, Abstract Syntax Tree, the reason we use that terminology is just that we want to talk about the overall structure of the program, right? So it is going to be actually tree structured, right? We'll start at some root node. It is going to be tree structured, and it is going to go ahead and actually represent sort of what we see in that source file, right? The programmer was typing in some kind of a file. It is going to look pretty close to that, but with a lot of the details of the syntax stripped out, right? So something like, oh, okay, well, all of our statements are ending with semicolons. We don't need that information anymore at this stage. By the time we are actually trying to manipulate some representation of the program, we don't really care how the programmer actually wrote it down, what syntax they used. And in fact, later on in the semester, we're going to see that we can use multiple different syntaxes for the same language. And in fact, y'all are all going to implement 2 different syntaxes for the same language. And so that is sort of a way of representing the core underlying constructs that exist in the language without bothering to represent, okay, and here were the particular characters that the programmer wrote down. And so that's why abstract is the first in AST. And what was the first part of the question?
Oh, I was just wondering, like, do optimizations like a loop unroll? I forgot what the other optimization is, where you take like a function and then put it in place where it's like reference.
Yeah. So I think this question is, do we want to do something like loop unrolling, inlining, the optimizations that we've probably heard of? Are those normally happening, oops, sorry, didn't mean to erase. Are those normally happening in AST land or on a representation of the assembly instructions themselves? Most of the optimizations that you will have heard of are going to be happening in AST land. So in general, we have a lot of information available to us at the stage where we are operating over some representation of the program that the programmer wrote down, that we no longer have available to us once we just have sort of this straight line of instructions. And obviously, there's a lot of other information available in instructions, like we are going to see things like jumps. We're going to have some understanding of how you might move between the various instructions in that sequence. But in general, there's a lot of information that gets thrown away when we are going from AST to instructions about how the programmer actually wrote this thing. And so most of the optimizations that you've heard of are probably happening in AST land. Yes, so that was such a good question. So this question was, when we say that we're going to have two different syntaxes, does that mean we're going to have two different ways for the programmer to write down something that will then get translated to the same AST? That's exactly what it means. And so that could even be for this case that I just showed you. You could imagine that we have one AST that represents these two programs, right, these two strings. But the user has clearly written down the programs with different syntax. Yeah, great question. But yeah, that would mean taking two different source codes, putting them through a different tokenizer, through a different parser, but then generating that same AST representation. Yeah?
To further differentiate between compilers and interpreters, do interpreters, like Hotspot in the JVM, do those have their own optimizations that aren't included in the
Oh, I think I understand this question. So I think this is a question about just-in-time compilation.
Oh yeah, like when we have just-in-time optimizations, like does that also fall into this, or is that?
So the answer is going to be some of the time. So in general, if you are running a program where mostly you're interpreting it, but you realize that there's one part that you are running a lot, you might decide, oh, I don't want to do this slow interpretation process for this part over and over and over again. I am instead going to actually run my compiler just on this snippet. And now, instead of running the interpreter on this every time I need to execute it, I'm just going to go ahead and run that now compiled code. Right? So this is basically saying we can mash together interpreters and compilers in really cool ways. Yeah, just-in-time compilation was one of the really cool things that came out of PL land in the recent past. OK, not that recent to y'all. It feels recent to me. Whatever. OK, cool. All right. We're not going to be going away from this diagram. This diagram is going to live with us. So we're going to come back to this. Don't feel like you have to get out all your questions about this for now. But hopefully, now that we've had that chat, we have some sense of why we are focusing on this difference between syntax and semantics. Because in fact, we just talked about the fact that two different syntaxes could lead us to this same AST, which means that we can kind of ignore syntax for a pretty long time when we're focusing on code gen. What we care about is semantics. What we care about is the behavior of the program. However, having said that, that's not going to mean that it's going to be easy to just mess around with a string representation of the program. And so I am going to have us start thinking about something that's more like an AST, something that is giving us some tree-structured representation of the program that the programmer actually wrote. And so I want us to go ahead and together stare, contemplate this slide with people nearby. And what I'm going to ask you to come up with is if you were trying to break down all these programs into sort of the fundamental building blocks that are appearing in these strings, something that you could use that maybe has not too many components, but you could compose all of these programs with them, what would you point to? What patterns are you observing about what's appearing again and again? So go ahead and discuss with folks nearby for about a minute.
If I make an announcement at the end of class, there was some disagreement about the homework 1 due date on GradeScope and the website.
Sure.
I fixed it, so I just want to quickly tell everyone when the homework 1 thing will be due.
Yeah, totally. Yeah.
Thank you.
So maybe to kick it off, what name might you give the things that I have currently highlighted up here in green? Yeah. Okay, I'm hearing literals. Can we maybe even be a little more specific here? But I love that answer. I'm hearing numbers. Yeah, so I would say these are number literals. That's great. So let's say numbers. What else are we noticing? What else might we be seeing here? Operators, I like it. I would love to group together our operators with some other things. So what if I highlighted this. I'm going to go ahead and have you discuss for 20 seconds with folks nearby. What might we call this? So I'm going to call that symbols, not a particularly specific name, but something that clearly applies to all the things I've highlighted in purple. What else have we got here? Yell it out for me. What else is happening? I'm hearing lists. I totally agree. And in fact, we've got even nested lists going on here, right? So here's a list. We've got this list right there. We've got this list over there. And then we've got this larger list over here. This entire thing is a list. That's a list. That's a list. It seems like we've got a bunch of lists going on. I'm sorry, I have not highlighted all of them, but hopefully we get the idea that the other thing that's happening here is lists. So that looks pretty good to me. We have managed to sort of boil down all these programs that are doing very different things into a representation that really only has these three ingredients. And so in case you have not seen these before, which is totally fine, these are called S expressions. So these were actually introduced way back in about 1959, 1960 by McCarthy, assistant professor at MIT, was starting to try to make this language, trying to make it easier to mess around with lists of information. That was going to be useful for the research that they were doing there. And so they had this idea they were going to have this be the internal representation, right? This was going to be that thing that was appearing in the middle of our compiler diagram. This wasn't going to be what the programmer was going to write, right? They had this plan that long term, in addition to these, the S expressions, they were going to make this thing called M expressions. But at some point down the line, someone made a parser that just took in these and started actually, giving that out to people. People started getting used to writing these, and then they were like, well, seems like it's good enough. I guess we'll just have people write S expressions, and that's why Lisp looks the way it does today. So that's what we're seeing when we see these S expressions. This is the structure that they have. Do we have any questions right off the bat about what's going on here? Yeah. What does the S stand for? What a good question. I should absolutely know the answer to that, and I have no idea. S expressions. I don't even know what the M stands for either, the one that they were going to show to the programmers. I'll look it up. What other questions we got? Okay, cool. So this is how we are going to be writing programs in our beautiful language that we're implementing together, our 164 lang, or whatever we may choose to call it. This is what our input programs are going to look like. This is what the programmer is going to write. Oh, it might have been, was it symbolic? Symbolic expressions? That might be what it stood for. I'm not sure though. I wouldn't swear to it. So okay, this is how our programs are going to look in our programming language. So okay, we've got these common elements that we're seeing. Now that we know what these expressions look like, how will we actually represent these in OCaml? Right? In some ways, a string does feel natural. We're programmers. We write our programs as strings. We're entering a sequence of characters into something, a file, a terminal, whatever. Right? So let's play around with that. What if we just do it as strings? So here we are back in our compiler that we played around with a while ago. Well, actually, I'll start by just reminding us what was happening in our compiler, because I know it's now been a little time since we last saw this. So the main thing that's happening, is we have this compile function, right, which the only thing that it's in charge of doing is coming up with the string that is going to represent our assembly for whatever program we put in. And we constrained it very tightly at the start. We said, OK, the only program that we're going to accept is going to be a number. Not a very exciting program. But we're going to go ahead and make the assembly that puts that number, whatever it is, into RAX. And so if you recall, RAX is the name of one of the registers that we have available. We only actually have a few registers available, about 16. And so one of the things that we're going to be messing with as we are thinking about code generation all along is how can we shuffle things in and out of registers in a way that makes things work for us, right? And so if we take a look at what's actually happening in this assembly, it's saying, OK, I'm going to make available a thing called entry. I'm going to make it available to the outside world. Well, why did we need that available to the outside world? It's because we have this runtime. We implemented our runtime in C. And C is expecting that there is going to be something called entry available. And it says, OK, I'm not writing my entry thing right here. Instead, I'm expecting that something else externally is going to provide it. Our assembly code is, in fact, the thing that is going to provide it. Oops, this was generated by a later version of the compiler. Ignore these. Pretend it looks more like that. So we would go ahead and say, OK, I'm expecting to see an entry thing. And our assembly code says, no worries, I've got your entry thing. And then we have this label. It turns out we are using that for starting a function. We'll later find out that we can use this label for other things. But we are using it to represent the start of our entry function. And then we have this move instruction. This is one of the x86 instructions that we are going to be able to use. It just says, go ahead and put this value 50 into the register named RAX. And then we have this ret instruction, which just says return control to whatever previously had control. So what previously had control? Well, it was the runtime, right? We called this entry function right here. And so control returns to right here. The C runtime chooses to go ahead and print out whatever got back from entry. What did it get back from entry? That's a little bit weird. We don't necessarily see anything coming back from entry. But in fact, what C expects is that it is going to find the return value of whatever it handed off control to inside that register RAX. And so what did we choose to do? Well, we chose to put the value associated with our program inside the RAX register. And so when runtime.c, our C program, chooses to look inside that register, it is going to find exactly what we wanted it to find. And that's how those things all tied together. And then we had a little helper function that was going to go ahead and pop all of that text associated with the assembly instructions into a file. And then we have a little other helper function that's just putting into a file, running the linker, and then getting us back the output from running it. So far, so good on what our compiler does. Yes? Why RAX? Yes. So we were not actually in charge of what register C is going to look at, right? So we could have chosen to implement our runtime in some other language, in which case we would have had to make sure that we were putting that value inside whatever register it is expecting to find the answer in. Because we chose to implement our runtime specifically in C, we had to know where C was going to look. You know, I go look through the documentation, I go find where it's expecting to look. It says I'm looking in RAX, so I say, OK, fine, I'm going to go ahead and put it in RAX. Now, when we are just communicating with our own programs, our own assembly that we have made, we can do anything we want, right? All bets are off. But once we're handing back control to C, at that point, we had better make sure to put in RAX. Thumbs up? Amazing. OK, so that's where we're at. So now let's go ahead and let's keep thinking about how we actually want to represent these programs, because I think that's sort of the key thing that we're going to wrestle with before we get to unary operators. So let's go ahead and look over here, and let's write ourselves a little expression. So let's do E1, and let's go ahead and say if x, y, z. Not a particularly exciting expression. It's a string. I guess that's OK. But say I go ahead and have another program. So say maybe I make something called increment, right? And I call it on 4, and I want to get back 5. So say this is what I've got as my two programs that I'm considering. What might make these actually pretty annoying to deal with if I am trying to process this string character by character? if I haven't done any processing to turn it into a nicer form? Go ahead and discuss with folks nearby. All right, so what I'm hearing as I'm eavesdropping on you all, sorry, is that it just seems kind of messy, right? Like say we're going ahead and we're looking at that first character and it's a paren. Okay, at that point we don't really know anything about what to do. So maybe we go ahead and we look at that next character. Okay, well, it's an I. Well, unfortunately, we still don't know what to do. It's an I here as well. And so then it can get even worse, right? Because what if we actually have a bunch of space here? That's actually fine, right? Like they should be allowed to do this, right? It just gets pretty messy having to keep track of all of this character by character, really just manipulating it as a string. We could do it, right? There's nothing saying we couldn't do it. But boy, wouldn't it be nicer if we had some other representation? And so if you remember, back during our paper exercises, we had this thing that looked like type project equals sample or dress of int or suit of int star int. What if we took advantage of the fact that we can create our own types, we can create our own constructors, and we actually made something that is going to give us a nicer, easier to manipulate representation of our programs. So let's go ahead and do that right now. Type sexp for sExpression. And let's go ahead and give us a number of constructors. I bet if you chat with someone nearby, you're going to be able to make some guesses about what constructors we would make available based on what we were just doing on the whiteboard. So feel free to turn to someone nearby and make those guesses. This also gets at some of the questions that I think we ran into last week where folks were asking, can our types be recursive? Yes, they can. And we asked, can we have lists of whatever length in there? Absolutely, no problem. So okay, this is starting to look pretty good. We've got our sexp thing, right? It doesn't look that different from the examples we were seeing before, right? Like this really does kind of look similar to how we've already made types last week. So hopefully this isn't scary terminology. Do we have questions about this sexp type so far? Okay, cool. It's okay if they come up later. Now, there is one annoying thing going on here, which is that now we have to go ahead and write out this E1 in a totally different way. So we're going to have to write it out something like LST, SIMIF, SIMX, SIMY, SIMZ. Okay, I don't love doing that, which hopefully means that all of you can figure out why we might want to have a parser, why that is a part of the compiler that we might be interested in having. So we will go ahead and see a bit later how we actually do that. For the purposes of today, we're actually just going to use sort of a really simple parser that is just turning this into, turning something like this into something like this, assuming we play nicely according to the rules of our spacing. Okay. So that's what we're going to be doing for now. Let's play around with this now that we have it. Later on, you will write your own parsers, but for now, even for homeworks, we're just going to give you a parser that's going to basically take care of turning something like this into something like this. But let's go ahead and see what we can do if we start representing programs in this way. So let's go ahead and do let which constructor, let's have it take an S expression. And let's go ahead and just use this to figure out which constructor we have used to create E1. And so based on the activities that you saw last week, I want you to take 20 seconds, discuss with someone nearby, what is the construct we're going to want to put right here? What's that first keyword we're probably going to want to type on line 10? Go ahead and chat. Anyone want to yell it out? I'm hearing match. I totally agree, right? This is the way that we've already seen for how we can check which constructor we use to actually construct. So let's go ahead and match E with, and let's consider if it's a symbol, in which case we can print a symbol, or if it's a number, or if it's a list, and take a moment to now predict which of these we are going to get for our E1. And let's call it on E1. Hopefully everyone did predict a list, right? That's what we can see, sort of that outermost thing right here. Okay, so now we've figured out which constructor. This is kind of a boring thing to do with these expressions, but maybe we can start doing something a little bit more interesting. Let's go ahead and try, this is going to be a really weird program analysis that wouldn't really make a lot of sense to do. Let's try just adding up all the numbers we can find in the program text. Boring, weird, but it's going to give us a sense of how we can start messing around with this representation of a program. So let's go ahead and let's still match all of these, but now suddenly we're actually pretty interested in producing a number, right? We'd like that to be our output. And so what do we want to produce if we see a symbol? I'm going to argue that's going to be a 0. What about if we see a number? Okay, well in that case we'd better give it a name because we probably want to produce the number itself as output. So let's go ahead and have n be the output there. What else do we need to do? Well, this is the one that's getting a little bit weird. Go ahead and chat with folks nearby for 20 seconds. What are we going to do inside this list case? I was hearing all the things I was hoping to hear in your conversations, but I haven't quite made it happy yet. Any guesses about why I haven't quite made it happy yet? That's right, I'm trying to call total, but I didn't tell OCaml that I'm allowed to use total recursively. So let's just make sure OCaml knows that it's okay to use it recursively. Okay, I want us to write one more of these funny little program manipulation functions before we take our break. But first, any questions about this one? Like again, this is a super weird program analysis. There's not really any reason why we would write this program analysis, but we can.
General question, why does OCaml not assume that a function is recursive by default?
Why does OCaml not assume that a function is recursive by default? In general, OCaml design tends to lean towards let the programmer express more about their intent, right? So you've seen cases, we've talked about the fact that you can add type annotations. We talked about the fact that you can put parens around things that don't necessarily need parens in order to communicate with the compiler. In general, the designers have tended to err on the side of let the programmer be in charge. Like there are things we're looking out for the programmer. So if you think of the match cases, right? We're looking out for those cases where those are not exhaustive. So there are definitely things that the language is trying to sort of guide you away from. But in general, errs on the side of making sure that the programmer is in charge, the programmer has agency. Yeah, good question. Okay, cool. I'm going to have us write one more of these. I also wanted to mention, now that we are playing around with this compiler again, I want to just remind you all, if you go on the website, you can find a link to the class compiler, the thing that we are all constructing together. It's all just going into GitHub. You can look at it at any state. You can look at it, the state right before we start class. You can look at the state after we do class. You're always going to be able to actually see this code base if you want it. So OK, let's go ahead and do maybe a slightly more interesting analysis here. So let's figure out if the thing that we are actually processing, if it has an if statement inside. So let's see. If we see a symbol, I'd say let's go ahead and have that be false, because we really don't want to see just a variable named if. Presumably that's allowed right now, a name that is if. We actually want to see an if that's actually appearing at the start of one of these lists, because we actually want to see if we have an if statement, or an if expression, actually. So let's go ahead and say false if we see a number. And then again, we'll have this actually be the interesting case. Again, please discuss for just like 20 seconds, what do we want to have in here? OCaml letting us do some cool stuff right here. So we've talked about the fact that OCaml is basically a really convenient language for building programming languages. This is one of the reasons, right? Being able to do something like this, where we're able to go in to the structure of the program that we're processing and say, OK, let's take a case where the first thing in our list is the symbol if. And then I don't care what it's cons to. It can be anything, whatever. Like, all I need to know is that that first symbol is an if, and then I can do true. But the compiler doesn't seem happy with us. We've gone ahead and created a match case for all three of our constructors. Why isn't it happy? Yeah, so what if we still have a list, but it starts with literally anything else, right? So we have not, even though we have made a case that starts with each of those three constructors, it is not yet exhaustive, because we could have a list that starts with, say, add one of our operators that we are going to be adding. So let's go ahead and do list L. And in that case, we just want to go ahead and basically descend into the children. So list.exists. This is just a nice little list function that's going to go ahead and see if any of the things that are being passed as input are true. So let's go ahead and do has if L. And this is just going to, oops, sorry, that's exists with an S at the end. That's just going to check if we can go ahead and get back true from basically exploring any of the children, any of the sub-expressions. So let's go ahead and save that. Let's run it on our little E1. I'm hoping everyone else like me is predicting that E1 is going to give true, since we do in fact have an if in there. But let's find out. Let's find out if that's what we get. So let's do has if E1. And it's true. All right. That's where we have landed on playing around with this slightly nicer representation of our program. Let's take our 5-minute break. We'll come back together at 4:36. And then we will go ahead and get into our Unary operators, the reason we have started wanting a nicer representation. Go ahead and take your stretch break, take your water break.
Professor.
Hello. Sorry, loud.
I was just going to say, I appreciate that whenever someone asks a question, you repeat it. It's like for the Zoom lecture.
I know, right?
A lot of professors don't do that. I appreciate
Oh
it.
dear.
So I
Okay.
just wanted to acknowledge it.
Oh, I'll try to keep doing it.
Yeah.
Okay, cool. Hi.
One of my friends want me to ask you that he has his application on September 2 to this class.
Okay.
He is a Globe concurrent enrollment student.
Okay.
And is that possible, like slightly possible that he may be enrolled in this class?
I think so. So they did increase the enrollment cap for sure. Yeah, I guess that might be worth making an announcement to have folks come up and give me their emails. Let me get a piece of paper. Tiny logistics note, if you are a concurrent enrollment student and you have not yet gotten the official invite into the enrolled class, please come give me your email right now just so we can make sure we get you in.
He hasn't sent me his email, so may I email you later?
Come to the next class session.
Okay, okay.
Yeah.
Yeah, I think, I'm trying to catch up with emails. It's in general.
Yes, if you're a concurrent enrollment student and you haven't yet gotten like the official invite into the class, just give me your email so I can make sure we get you in. Amazing. Yeah, I think David can't actually push that one through, I think. We'll check. Maybe he can. I don't know. That'd be great. That would be great if they could do it.
I haven't filled the enrollment form.
Ah, okay, so I can't put you in until the enrollment form is in, but once it's in, then I can get, yeah.
It should be done tonight.
Perfect, perfect. Yeah, thumbs up.
Where can I get the access to previous recordings?
Oh, I don't know. What do you mean by previous occurrence?
Previous recordings of this class, because I just
Oh, it's all on the B courses. Yeah, yeah, thumbs up.
I want to get all three emails, so I need to write my email here.
Yes, yes, thank you.
since tomorrow is due like 5 days ago, can I like submit it like right now or?
Yeah, just go chat with David and they can get you an extension.
Okay.
Yeah.
And the score will, or can I get the regular score?
Yeah, yeah, just get the extension and that all goes, like, once you get an extension, it's all just graded normally. Yeah, as if you, yeah. Amazing. Go ahead and jot that down. Tell him to start coming to class, though. Tell him to start coming to class. You okay? All right, let's come back together. So I'm hoping that the particular unary operators that we are adding here today are not going to be super confusing. They are unary and that they are taking a single argument, right? There's one operand coming in. And since what we have right now in our language is numbers, it's numbers that are going to be going in. And the only thing we're going to be doing is adding one or subtracting one. As you may predict from the names, add one adds one, and subtract one, sub one, is going to sub one. So hopefully we're pretty much on the same page about how those are going to behave. Let's go ahead and figure out how we can actually make our compiler do this. We're finally extending our language to do more than just having programs that are numbers. So let's go ahead and swap to looking at our compiler. We have access to a little convenience thing that is going to do our parsing for us, as I mentioned. So I'm just going to show off how that works. So we've got our little OpenSX thing. We can go ahead and say parse this. It is really not doing anything particularly interesting in there. And as I said, we are going to get to parsing later in the semester. So we're not even really going to take a look in there. But what you can see is that it is going ahead and making things like what I wrote out manually, but it is making them automatically for us so that we can continue to write things in this nice familiar way. And what we get back at the other end is this nice structured representation. So I'm going to go ahead and start having us use that here in our compiler. So let's get rid of all the stuff we were playing around with. And let's use that same SX thing right there. So OK, now we have that. The next thing we're going to want to do is make sure that our compile function, the thing that is actually generating our assembly instructions, is taking one of these as input. So let's go ahead and change that from string to sexp. OK, now what is going wrong? Well, first, we've been expecting a string there. But also, suddenly, we're accepting programs where it's not going to be sufficient to just go ahead and pop everything into this one slot in the program. But let's go ahead and start with just first fixing this up to still handle the programs we could fix in the past. So I think there's probably an obvious way to start that, which is let's add one of those matches that we've been using. So match program with, and the one that we already know how to handle is if the whole program is just a number. So let's start there, num_n. OK, great. That's the situation where we want to do this. We can't just use the entire program. We're going to have to use n, and we're going to have to change our string formatting. And then so far, so good. Now, obviously, OCaml is complaining. This is not exhaustive. So let's go ahead and make sure that we can communicate when there's a program that we don't yet know how to handle as input. So let's go ahead and add something that we will call a bad expression exception. So bad expression of sexp. And this is just going to be our way of saying, hey, honestly, I don't know what to do with this. So if we get anything other than a number, a single number, as of right now, our compiler doesn't know how to handle it. And so we'll go ahead and say, whoop, raise bad expression for that expression. We just don't know what to do. OK? We're getting pretty close here. OCaml is giving us a little bit of a hint about something else that is not going right. So what is that? Well, we've got this program that's getting the red squigglies. Why is that? Well, it's getting a string as input, right? And so we're going to have to go ahead and make sure that what we're passing to compile is not a string, but is one of these S expressions. So let's go ahead and just call parse on that. OK, now it seems to be happy. So let's just make sure that everything is still working the way we expect it to work. Let's try running this. We'll make sure that we can still make our tiny little programs that just have numbers. So we'll do open the compiler, and let's do compile and run 33. Nice. OK, that still works. We've also gotten another little side benefit here, which is if you remember, before we could still run things that shouldn't have been allowed as programs. But now, we're getting our little bad expression exception. Now we get all this other random nonsense as well, but we're getting the thing that we wanted. So basically, we've already gotten a little side benefit from having this nicer representation of programs. So we seem to be going in a good direction. But there's still more we want to do, because it turns out we want to actually add these other things, right? Like we don't just want to handle only numbers anymore. So let's see what we can do. let's see if we can go ahead and start doing something maybe a little bit like this, right? So let me put a proposal here, right? We can go ahead and have a match that is going to go ahead and actually handle the situation for our add one, right? We'll have our list, we'll have our add one appearing first, but we go ahead and actually do the addition before we pop in the n. So if we take a look at one of the concrete programs that we were looking at over on the whiteboard, this would basically be saying that for this program, add 150, we could produce assembly that looks something like global entry, move RAX 51 ret. So what I want you to discuss with folks nearby is this a nice piece of compiled code to produce for this program? Do we like that as the output? Is this the thing we should make? Discuss for about 40 seconds.
So she's saying if we implement our program such that we add we perform the add one and kind of like compile step, right? So how to compile it to be entry, RAX, is that but like we're not guaranteed to have a number there. We can't just call the number to it. Thank you. We can't have that. But just list it. How did we remember? First, we generate assembly. Yeah.
All right. So I want you to go ahead and hum if you think, yes, we are happy with this output. And hum if you think, no, we are not happy with this output. Yeah, okay, so we've got some uncertainty, and I think that makes a lot of sense. So I think the people who are humming for no are probably thinking of a program something like this, right? So in another few weeks, we're going to get to accepting input from the user, right? We're going to have this little read construct, and that's going to allow folks to go ahead and enter some input right at the command line, right? And as soon as that is happening, trying to produce something like this becomes impossible, right? We're going to have to go ahead and make sure that the compiled code itself, the assembly, is in charge of doing the addition for us, because we won't know the value in advance, right? Now, I also get why folks would hum for yes here, because in this case, for this particular program, we can in fact figure out at compile time what value is associated with actually doing this addition. And so eventually, even later in the class, we are also going to see how there are optimizations that will let us change from something that is doing the addition right in the assembly to something that goes ahead and just puts 51 directly in the assembly, having figured out that this is one of those cases where we do know all of the values in advance. But as a general purpose way of handling it, we don't want to jump straight to just assuming that we can do all of the calculations at compile time. We have to assume that we're going to need to be able to do it at runtime. So okay, let's go ahead and look back again at our compiler. And basically what this is making me think is we are about to start having to interact with a bunch more assembly instructions, right? All we've seen so far, really, we've seen some directives, right? This is the thing that's declaring that we have this entry thing available, that's a directive. This thing that's just a label, that's a directive. But we've only actually seen 2 instructions so far. And so I'm going to have us quickly take a glance at this little library that we are going to be expanding over the course of the semester of the directives and the instructions that we are going to be allowed to have, right? So we are going to be able to use this global that we've already seen, this label that we've already seen, this move that we've already seen. But today we're also going to need to have access to add, to sub. We've already seen ret. So these are the x86 instructions that we are going to be allowed to use over this course. And in fact, we're actually going to have more that will be coming in. We will have a resource posted for you on the website of this particular subset of x86 instructions that we are using in this class. But these are all the ones we're going to need for today. And it turns out that just as we actually used this nice sexp library in order to have a nicer representation for S expressions, we might want to do the exact same thing for our nasty assembly that we've been building up, right? Building up this string directly is pretty gross. We might want something like this exact library to handle some of that for us, and that's exactly what string of directive is going to do. That is just going to go ahead and take in some directives and actually produce the kinds of strings that currently we've just been building up manually. So let's quickly adapt our current compiler to make sure that we can actually do the same thing but with this nicer representation. So let's open ASM, which is just to say open this file that we just looked at. And let's go ahead and replace what we're doing here with something a little bit nicer. So let's have this be global entry, label entry, move, register RAX, our immediate N, and then our return. Now, this isn't quite correct yet. Any guesses about why? Please yell it out.
You actually use the assembly instructions?
Yeah, so these are not a string, and we promised we were going to have a string. So we had better actually produce the thing that it actually can be consumed by our processor, which is exactly why we have this string of directive function here that's just in charge of taking this representation and turning it into the representation that we can actually pass on to our own processor. So let's go ahead and make sure that we are calling that. We're going to get introduced to something a little bit new. We're going to have this pipeline, right? So this is our little pipeline, and I'm going to show us how we use it, and then I'm going to talk us through what's actually happening here. So list.map string of directive, right? So that's the thing we just talked about, the thing that is in charge of turning things that have this directive type into a string. We're going to go ahead and pipe in whatever we get back from that into string.concat specialized with /n. Now this is a little bit weird, because if you remember string.concat, you might recall that normally what's happening is we have string.concat and then one character, and then a list of strings. Sorry, one string, and then a list of strings. And we're going to go ahead and sort of join them together with that. So why is this working? We don't have this second argument here. So this is working because of partial application. I'm going to show us another example just so we get a little bit comfortable, because this is a trick that we're going to be using throughout as we are writing programs in OCaml. And basically, it means that what's happening here is that we are making a specialized version of string.concat where the first argument is assumed to be this /n. So I'm going to show an example that's just with a different function. So let's go ahead and let's take a look at the type of list.map. OK, what we're expecting is we're going to have a function as the first argument. The second argument is going to be a list, and then the output is going to be a list. But we can go ahead and actually specialize this. So let's try doing that. Let's do list.map fun x plus 1. Now, the type of this is just a list to a list, right? That function is no longer part of the type anymore, because we've gone ahead and sort of baked that in. So we can give this a name. So let's call this specialized. And this is just a new function that we have available that is just going to add 1 to all the items in a list. So we can go ahead and say, OK, specialized, if I can spell, 1, 2, 3. Great, it has added 1 to each of the items in the list. So now that we have seen this example, where we're seeing, OK, we've started with list.map, and we know that the type of list.map is we get a function as the first argument, then we get a list, and then the output is a list. But we were able to specialize it by just providing that first argument in order to make something that is just going to take a list as input and produce a list as output. Now I want us to translate that to this string.concat example. I'll show you the type of string.concat. And what I want you to do is, with folks nearby, go ahead and predict what is going to be the type of string.concat when we're providing that first argument. Discuss for 20 seconds. Remember that we read this as this is the first argument, this is the second argument, this is the return. All right, does anyone want to take a guess? Fortunately, we don't need to guess. Oh, Campbell will just tell us. It looks like that is going to take a string list as input and produce a string as output, right? And so this makes sense because we can take a look at what was happening before. We were going to get that string as our first input, then we were going to get a string list as our second input, and then our output was going to be a string. And this is doing the exact same thing, except that that first string input has been fixed. We have fixed it to be /n. And that's what's happening here. We have this weird little specialized function that we've made right there that is just saying, OK, I want to go ahead and pipe in whatever I'm getting back from this previous section, pipe it into this specialized function that's just going to match everything together with the /n. And so that's what we're doing when we have the pipeline, is rather than putting the list.map on the outside when we don't even have the list yet, putting the string.concat on the outside when we don't even have the list yet, we can instead use this pipelining, which says whatever happened before, go ahead and pipe that into list.map, calling it with string of directive, and then calling it on this list. And then whatever we get back from all of that gets piped into string.concat, matched together with a /n. So this gives us a slightly more sort of linearized way of looking at what is happening as we go through this sequence. So OK, this is starting to look a lot cleaner, but we still haven't actually created our add1 case. So let's start work on that. We might not actually manage to finish before the end of class, but let's see how far we can get. So if we say list sim add1 arg, what would you and the person nearest you, physically closest to you, what would you say is the next thing I should write here? Please chat for a minute. This is not the answer. This is not the answer. So why is what I have just written here not a good solution? Yeah, this is all well and good if what we have right here is a number. But the whole point of writing these programs is that we can recombine these constructs over and over and over. So if I can switch us back to the whiteboard, right? What I just wrote there is going to work great if we have add 1, 50. No problem. if we have add 1, 50, all of a sudden this is that argument. And that isn't just a number. We can't just pop that whole thing right into the appropriate part of the assembly template that we have made up together. So what is the right thing for us to do? I'm going to ask you to sort of contemplate it with folks nearby for 20 seconds. So,
Like instead of num n, say like, yeah, I don't know, online ten, like instead of num n, we should either match with a number or another expression. Like I said, I don't know the syntax without the return. Generally, I think that's instead of expecting just a number, you want to check if it is a number, it can be not. If it's not a number, it can be.
all right, so I want you to hum if you think that we should do one pattern for add 1 n, another pattern for add 1 n, another pattern for add 1 n. Hum for that. Okay, well, we've got one vote. That's great. What about for maybe this is a case for recursion? Yeah, I have to agree. And so we're going to have to do a little bit of refactoring to make that happen. In particular, you can see that we've got this sort of front matter that's happening, right? We've got this global entry, this label entry. Those are things that should happen only one time. We've got the thing that's actually returning control to our C runtime. That should only happen one time. So let's start in on the refactoring that is going to make this a lot easier for us when we actually add our add 1 operator next class. So in particular, let's go ahead and have something that's just for handling the teeny tiny component that's specialized for the particular expression we're handling right now, whereas we'll have a little wrapper. Then that should take care of putting those front matter, that sort of boilerplate together for us. So that will take in our program of type sexp, and we'll go ahead and have it produce a directive list. So let's have directive list. Let's have it produce that. And then what are we going to want to do? Well, actually, you know what? Let's have this produce a string. We'll have this produce a directive list, and then this can produce a string. And that's going to save us some trouble in terms of not having to mash everything together in each of these cases. We can go ahead and have this sort of wrapper function that's in charge of that. So let's just real quick see what's going to be happening in here. It's going to look a lot like this, right? We're going to want to have the same sort of front matter that we had before. Now, this was specific to the particular instruction we were dealing with. So let's go ahead and get rid of that. And let's go ahead and start mashing together these lists, right? So here we're doing the thing where we turn it into strings. Here we're doing the thing where we actually mash it together with our /n. But we do want to have something in the middle here. Does anyone have any guesses about what's likely to go in the middle here? I'll give you a hint. We've got something else available to us. Yeah, so I think that's where we're actually going to get the code that is going to be specific to the expression that we want. So let's go ahead and call compile exp. Let's call it on sexp, the thing that we were getting in as input. Right now we don't have anything that's specific to that. And that is what we're going to do, which means that next time when we pick up later, oops, sorry, we called it program.